Hi, welcome back to the channel. So this is permeability of soil and flow nets. So this is worked example 2.1, pore water pressure and effective stress in a soil mass. Explain the terms effective stress and pore water pressure when applied to a soil. I don't think you can do that without talking about total stress. A layer of sand 5 meter deep overlies a thick bed of clay. Draw diagrams indicating the total and effective stresses and pore water pressure on horizontal planes to a depth of 9 meters below the ground surface. If the water table is at ground level, if the water table is at ground level. Sorry, I'll read this again. A layer of sand 5 meter deep overlies a thick bed of clay. Draw diagrams indicating the total and effective stresses and pore water pressure on the horizontal planes to a depth of 9 meters below the ground surface. A, if the water table is at ground level. B, if the water table is 2 meters below ground level and the sand above remains saturated with capillary moisture. C, if the water table is at the top of the clay and sand above dry. Unit weight of sand 20.9 kilonewton per meter cubed saturated and 17.4 kilonewton meter cubed dry. Unit weight of clay equals 17.8 kilonewtons per meter cubed. Solution, I just put it right at the bottom. The total vertical stress sigma on any horizontal plane below the surface of a soil mass unloaded, except for its own weight, sometimes referred to as the overburden, is equal to weight of overlying soil, area of plane. Thus, the total weight W on plane XX in figure 2.1 is W equals gamma Z minus ZWA plus gamma sat ZW dot A. Therefore, total stress sigma equals W over A equals gamma Z minus ZW plus gamma sat times ZW. Ground level Z, ZW, water table, unit weight, unit weight area, X equals area. Hold on, so diagram figure 2.1. The total weight W on a plane XX in figure 2.1 is W equals gamma, that's Z minus ZW times area. Z minus ZW area. Z minus ZW times A plus gamma sat times ZW. Oh, right, yeah. All right, the total weight on a plane XX is, so it's the weight of the, so it's just the weight of the soil above the water table, which is the area is the volume times the density, and the volume is the area times the height, and the height is Z minus ZW. So W equals the weight of the soil above the water table plus the weight of the soil and the water below the water table. Gamma sat is the weight of the soil and the water because it's saturated. So gamma sat must equal more than 1,000 kilograms per meter cubed. Thus, the total weight W on plane XX is given in figure 2.1 is W equals gamma Z minus ZWA plus gamma sat times ZW times A. Total stress sigma equals W divided by A. W divided by, oh yeah, so you just take out the A's on both sides. The total stress is the weight per area, isn't it? Equals Z, what, gamma Z, oh, hold on. Gamma Z minus, gamma bracket Z minus ZW bracket plus gamma sat times ZW, and Z, oh yeah, so that's alright. Right, okay. So that's all there. Your total stress sigma, it could be simplified as gamma Z minus gamma ZW plus gamma sat times ZW, which is also equal to, yeah, gamma times Z minus, oh yeah, you could change it around a little bit. But that is basically the equation. Oh, in this little drawing, say in this little diagram you want to find, they should do an example of this in, because you've got so the above it will be like a hydrostatic and lateral soil pressures. Well, I might draw that out as well in another little video, so that people can understand what they're talking about. That's the first example to do, isn't it? Right, so the total stress can be divided into two distinct components. One, the effective stress sigma dash, and the pore water pressure U, both of which vary linearly with depth. The effective stress and the stress transmitted through the points of contact of the solid particles of the soil. It is known as the effective stress since any change in sigma dash produces a change in the volume and shear strength of the soil. The pore water pressure and the pressure exerted by the mass of the water in the void of the soil above and below the water table. The pore water pressure is the pressure exerted by the mass of the water in the voids of the soil above and below the water table. It is also referred to as the neutral pressure, since any change in U, pore water pressure, has no measurable effect on the mechanical properties of the soil. Under equilibrium conditions, i.e. when there is no flow of water through the soil, the total vertical stress sigma on any horizontal plane is made up of these two components: the effective stress sigma dash, the pore water pressure U, and the relationship can be expressed avatexagi as sigma equals sigma dash plus U, which is a fundamental one in soil mechanics. At the water table, U equals 0. Above the water table, if the water in the voids of the soil is held by capillary action, the result is an increase in the effective stress due to negative pore water pressure. So this is, so on this sheet, we've got the right, I'm going to have to do a separate video on this one, because this is quite yeah, it's got quite complicated, isn't it? And there was three conditions. One with the A is when the water table was at the ground level. B was when it was, wasn't it 2 meters under? And 3 was it when it was at 5 meters under ground level, below ground level, I mean, under or below. For the given data, the total stress sigma, the pore water stress U, and the cap are calculated at the levels where the conditions change. The effective stress sigma dash is then found by subtraction using equation 2.1. The results are tabulated in table 2.1. Since the stresses increase linearly, the stress diagrams can be drawn as shown in figure 2.2. So what I do is I go through these in a separate video. So they've got the depth along the top, and then the pressures, the total stress, the pore water pressure stress, then the effective stress for each of the water table levels A, B, C, and then it goes through it. What I do is I do a separate video on that, and I'm going to colour it in because I think it makes it stand out a little bit better. Okay, I hope you enjoyed this video and the last one. Please see me in the next video, because then I'm going to explore this. I'm going to do the video of this table and the diagram, and also do a little diagram on this one as well. It's good to start with the really simplest cases, and then you can understand. Oh yeah, so I'll see you in the next video. Please like this And then please like this. Please like this video and then subscribe to the channel so I can keep on making videos. If I'm gonna, this is the soil mechanics section, but I'm also going back to the structures, the stiffness method. Hopefully you can find this video helpful. Thanks for watching. See you in the next video. Bye.